All right. So this week we're going to talk about J Hook vanes. So a number of you on the line have built a bunch of these before, and I think everybody has a pretty good understanding of a J Hook vane. So I'm going to kind of go through it fairly quickly here, and then if you have questions related to what we go over, let's bring them up at the end. J Hook vane is oriented 20 to 30 degrees from the tangent bank. These started from the idea of a barb, um, a river barb, and at that point, river barbs were more abrupt in the channel, sometimes as much as 90 degrees into the channel. And they started sloping upstream. We saw downstream scour from these barbs, and a lot of these barbs came from near shore sedimentation issues on beaches and shorelines. Um, they slope up from the channel invert at a 3 to 5% arm. This has also changed. Originally, some of the cross channel vanes actually pointing the downstream direction, whereas now they point in the upstream direction. And they may control grade using, we can control grade using a J hook, and we have to limit drop over these J hooks based on the materials being used. And we may need footers, sills, geotextile to avoid piping or washouts or failures. So we can have boulder vanes, a single arm vane, and a J hook. Uh, a single arm vane is just an arm that is constructed on the bank of the channel. There's nothing that goes across channel. It just stays on 1/3, the closest 1/3 of the channel. Sometimes they move farther in towards the center of the channel, but it's just one single vane arm. And these are also been designed as barbs in the past where you use smaller material. A boulder vane will use a very large boulder, make sure it's designed so that boulder does not move, whereas barbs sometimes will use a riprap that could move at a certain flow. But boulder vane will focus on a 20 to 30 degree angles from the banks, essentially working like a runway ramp for a truck. So it slows down to allow sediment to deposit. So essentially, if you're a truck going down the hill, you move off to the side so that you can stop, and that sediment will move off to the side so it can stop. Here's a structure we built on the Davison River about 15 years ago in Transylvania County, North Carolina. And there's a scour hole downstream of this, and you can see the deposition on the upstream. A lot of this was placed, but there is some fine deposition that's placed underneath the rocks after the J hook was built. This is a boulder. This is the same boulder cross vane at the J hook at the this boulder J hook at the Davison River at high flows. Log vane arms. We generally were building them at 2 to 3% now. At one point, we were building them up to 10%, and I used to see a J hook. I've seen some J hooks a long time ago spec'd at as high as 15%. But right now, we're trying to stay below the 4% slope on arms, and this will change based on substrate that we find on reaches too. So it doesn't mean that we can't build a steeper arm slope, but in general, we try to keep it close to that 2 to 3%. A lot of the log vanes were moving closer towards a more gradual angle horizontally, 20 to 25 degrees. And for all log vanes, we use geotextile and backer logs. We don't really get away with not using the backer logs. The J hook's going to create an undercut feature for these for this log by using a backer log instead of a footer log out in the front of it. So we press a backer log underneath it. What that looks like in detail is that if we look down at the bottom section here, that the log is actually behind the header log. So it gives you protection for scour, but it doesn't give you any kind of a balance for the log on top of it. The log on top of it is pinned in place and cantilevered out by being anchored into the bed and anchored into the bank. So here's a log J hook being installed by North State Environmental. And then here's another log J hook on a smaller creek. You can see the undercut bank. This has a root wad combo that The root wad kind of holds up the slope of the arm, so you can place the root wad, and then the arm can be placed on top of there to give you your 2 to 3% slope. We direct flow away from the edge of the banks. It's a J hook can be grade control. Brush toe can be buried underneath the log, and backer logs and geotextiles are needed for a log J hook. A log J hook. A couple of things that we look at is the hook boulders control grade, the footer boulders and geotextile, and the boulder sills are also very important for making up the log J hooks. So we generally don't build log J hooks without having to still have boulders involved in the structure. So here's another example of a log J hook. So here's some vanes that we installed a number of years ago. This is a picture of me in 2007 with Eve Brantley down in Auburn, going down the banks, and we wanted to stabilize this bank. Right where Eve was standing up on the top of the bank was a sewer line that we're trying to protect, and the river was eroding into that sewer line, so we wanted to build in a number of multiple vanes. So in 2008 we got done. North State Environmental did the construction with us, and you can see the truck up there's on the same roadway where Eve was standing before. So we regraded the bank, we put in a series of multiple vanes. By January of 2009, we started to see some revegetation. By July 2009, we had a lot of revegetation. And then in 2012, it's hard to tell kind of that the bank was eroding at one point, and you can see how the water is getting deflected away from the banks over these vane structures. So a couple of failure mechanisms that we see with log J hooks is we see flanking. As we see flanking, usually that's related to the length of the sill or gaps in the boulders near the sills. We see scour and movement of boulders. Sometimes this is related to too much drop or improper footers on the boulder. So we've definitely seen times where footers have been too small, or there's been a gap in the footers, so then the header had too much drop on it and it created a scour and then rolled a rock. Sometimes we have scour and movement of boulders because the boulders are just too small. So we just have boulders that are too small. Sometimes we've even seen them because the boulders are the wrong shape or the wrong density of rock. So sometimes you get a lighter weight rock, or you get a rock that doesn't have much resistance because it's a smooth quarried rock that's more like a tombstone or headstone than it is a natural rock. So it basically just slides on a smooth surface instead of giving you resistance as it tries to roll. And then we see scour movement of logs, but a lot of times this happens because they're too short of logs, or they haven't been anchored into the bank, into the bed. And this doesn't mean anchored by like a duckbill anchor. You can do that, but in general, I don't recommend that. I just recommend anchoring them by burying them far enough into the bank and into the bed for the construction. And then we also see scour movement of boulders because protrusion above the bed of the channel for the log and the boulders are such that they create a scour depth downstream that exceeds the footer depth. And then we basically see movement of boulders because it's just getting scoured because of the protrusion above the bed of the channel. This doesn't mean there's a drop over the structure. This means that as you are on the bed of the channel, if you were rolling a car on the bed of the channel, you would hit a rock and you'd have to go up over that rock. That's what protrusion is. Doesn't even mean there has to be a big drop over, but protrusion still creates scour on the downstream side. And then we also see near bank erosion. A lot of times this is related to limited bank protection from a horizontal angle. So we'll have a horizontal angle that's just off. Maybe it's too abrupt in the channel, and then we don't get as much bank protection. It can also be caused by having a rock out of place on the arm, and then you'll have bank erosion from that. Then we also see piping, which is usually related to gaps in logs or boulders, exclusion of fabric, or backfill gradation being improper. So that means we may just have really fine material for the backfill gradation, or we just don't have, we have a uniform gradation, or maybe we have too small of a D50 in the gradation. So these are all things that we've seen for failure mechanisms for J hooks in the past. In general, they're still very successful. structures, but it's important to know that there are some failure mechanisms associated with that. Um, so we're going to talk now. Luis is going to give us, is going to add in the talk this week, and he's going to talk about rock structure cost estimates. So we came up with a project in Nebraska this week where we were looking at a contractor brought in boulders and got through about half the structures and realized they were out of boulders. And we just put together this little presentation on the difference of rock structure cost based on choice of boulders. I think for a lot of the guys on the line here, this is going to be pretty remedial in the sense that you've seen this before, but maybe not, or maybe there's something you can add to it. So Luis, here you go.
Good morning, everyone. I'm Luis. You didn't hear that before. What we came across in this project was when placing the boulders for the J hooks. The boulders don't come all in one dimension. Usually, when we put in the plan sets, well, the boulders are from 2 to 3 feet in diameter, average diameter. As you can see in the pictures on the right side, the boulders don't come in a single size. As you can see, you have different sizes and different shapes. And we want to place those rocks along the J hook. That's going to make a difference how many boulders you're going to need to build the structure. For a J hook, or to build the structure, assuming the length of the structure is about 60 feet, and we assume you're using a 2 feet diameter boulder, we get a average volume for per boulder about 8 cubic feet. And for this structure of 60 feet, the total mass would be 20 tons. And the cost, approximate cost, would be about $2,000 to build this structure, assuming the cost per boulder or per ton is about $100. Well, what happens if you use a larger boulder? What about if you use a 3 feet diameter boulder? Well, your volume will be about 27 cubic feet. The total mass for this structure will be about 45 tons, and the cost for this will be about $4,500. Just using 2 different size boulders, the cost increase of about $2,500, which is an increase of about 225%. So it's always good to keep in mind what type of size of boulder you want to use. We measure all the boulders that was used in one of the structures. We use 16 boulders to build one of the structures. As you can see, we measure the width, the length, and the height of each boulder. As you can see, we have different diameters from 2.3 up to about 7 feet in difference. So this is quite a big difference. If we add up all the mass for the boulder, it's about 56 tons for 16 boulders. And assuming this $100 per ton, this structure costs $5,600. Well, we plotted the average diameter boulder versus the boulder structure cost per linear feet. How much would cost you? How much would cost to build a structure if the average diameter of the boulder is between 2, or in this case up to 10. For the case that we see previously, the smaller boulder diameter was about 2.3 feet, and that will put us at the lower end. And the cost per linear feet will be about $60 per linear feet. And upper end, which was about 5.7, the cost per linear feet would be about $270. So using a different size diameter of boulder will make quite a big difference at the end cost, which is something need to be taken into account when we put the plan sets. As you can see in the plan sets, we should have said for well, the boulder diameter is going to be from 2 to 3 feet in diameter, and approximately the total weight will be about 52. Oh, in the bottom, so that's about 40 tons per habitat or per structure, which put us about in the $4,000 per structure. Any comments, questions, concerns? Thank you.
All right. Well, I guess if we have no thoughts, we want to put together that the quantities and appreciate Luis helping us with that today. It was one of those things we came up with this week with the contractor and thought, well, it's probably good to document it. I think a lot of us have kind of known that before, but don't always have it as clearly demonstrated as what Luis had put together today. So. All right, well, we'll stay on the line here today, and I appreciate everybody taking your time this morning. Have a great day, guys.
Have a good week, Dave.
Yeah, thank you, Jonathan.
Nice work, Luis. You guys have a good day.
Hey, you bet, Greg. See ya.
Yep.
Bye, Dave. Bye, Luis. Good job.
See ya. See you, Gina.
Have a good week.
Hey, Rich, you still on? All right. Well, have a great day, Rich.
Trying to get out of here. All right. Yeah, you too.
Yeah. Hey, when do you want to present on that, or just somewhere down the road on the project?
I probably need. I mean, if you want to do it, it's a matter of just putting something together real quick. But probably I'm really busy this week. I don't know. Maybe November.
Yeah, it sounds good. How about can we tentatively put on there November? I think. Let's see, November 2nd, 9th. How about November 16th? Does that work for you?
Yeah, the only thing I have is a river shared at 6 o'clock on that day. So
Yeah, that's good. I guess you can do that still then.
all right, cool. Thanks.
All right. Hey, we'll see you. Thanks a lot, Rich. Bye.
Yeah, all right, bye.
All right, man.